In this video, we're going to discuss Bernoulli's equation. Now we're going to find out that Bernoulli's equation is an extension of the conservation of energy, which means we're going to start with our work energy theorem that we derived earlier in the semester, the idea that work is equal to force times displacement, which is going to relate to the change in energy. Now I'm going to write this slightly differently because we're going to deal with small incremental changes of mass, because remember in the previous video you should have seen with the equation of continuity that we had mass flowing through the pipe at a certain rate. So we had so much mass going through the pipe at a certain period of time. Alright, so now what I'm going to do is I'm going to do a little bit of rearranging, because as we learned at the beginning of this chapter, we are going to want to talk about pressure rather than force. So that means we need to get our force times displacement in terms of pressure. And we're going to do that by using the fact that pressure is equal to force divided by area. So this is going to equal our change in pressure times area, and then we still have our delta D in there. And then we're going to rewrite that as the change in pressure times the change in volume, because area times displacement is going to give us a change in volume. Because as you push down on something, you're compressing it, decreasing its volume. As you stretch something out and increasing its length, you're increasing its volume. Now, there's a minus sign that we have to add in here because pressure and volume are inversely proportional to each other. Alright, and I'm just going to recopy everything from the top down. Next, we're going to divide each term by dV. So we're left with just dP over here. And remember, mass divided by volume is density. So that means that we can replace the mass and volume I'm dividing by with the density. So that's what I'm going to go through here and do. Alright, so negative dP is the negative change in pressure, or we could write that as P1 minus P2, so reverse from what we're used to. And I'm going to replace the final and initial, which is 2 and 1, just to keep things more consistent. So this one should be a 2, this one should be a 1. Alright, and then I'm just going to rearrange things so that all the 1s are on one side. And all the 2s are on the other. So now instead of conserving energy, we're conserving pressure essentially. But it comes out of the concept of conservation of energy. All we've done essentially is take our work energy theorem that we learned earlier in the semester and divide both sides by volume. Now one thing I'd like to add here is we learned the equation of continuity, which was A1 V1 equals A2 V2. So these equations can be used in hand, because this would be V1 and then this would be V2. So these equations do go together. Now one thing that's not as intuitive is the relationship between pressure and velocity. So you can already see I have compressed the size of the tube that the fluid is flowing through, and you can visually see that the velocity is greater. So let's put a speed monitor and we can actually see this is 6.2. We don't want pressure yet. And this one here is 1.5. So you can see as we decrease the radius that indeed the speed increases. But the pressure is not quite intuitive. It's always instinctive to say as pressure increases that velocity increases. However, let's test that out. So we can see in the larger part of the tube that it's about 119, almost 120 kilopascals. But when I put it in the center, here, it's down to about 103, almost 104 kilopascals. So you can see as velocity increases, that pressure decreases. You can see this one's almost straight up. This is actually a little bit further over on the dial. So as velocity increases, pressure decreases. It's actually inversely proportional rather than being proportional.